In this lecture, we will find out input and output impedances of common emitter fixed bias configuration. This is the BJT amplifier circuit, and you can see fixed bias configuration inside the rectangle. In case of DC analysis, we only have to consider the circuit inside the rectangle because capacitors C1 and C2 will remain open circuited for DC, and we generally use DC analysis to find out operating point. We find out operating point in DC analysis, and we also find out input and output DC currents and voltages. But here we have to perform the AC analysis. Vs is the input voltage with resistance Rs, Vo is the output voltage, and it is the voltage across the load resistance RL. In order to find out input and output impedances, we need to do two things. The first thing is to find out AC equivalent circuit, and the second thing is to replace the transistor, this transistor symbol, with its equivalent model, and we are discussing RE model, so we will replace the transistor with the RE model. And as we are having the common emitter configuration, we will have the common emitter RE model, which we have discussed in the last two lectures. So let's move to the first step, in which we will find out AC equivalent circuit. In order to find out AC equivalent circuit, all the DC sources must be short circuited. We have VCC as the DC source, so we will short circuit VCC, and after this we will have potential at this point equal to 0 and potential at this point equal to 0. So we have ground at this terminal and ground at this terminal. Potential of ground is equal to 0 volts. This is the step number 1 in finding out AC equivalent circuit. In step number 2, we need to short circuit all the capacitors in this circuit. There are only two capacitors, C1 and C2. C1 and C2 are called as coupling capacitors. C3 is not present in this circuit because C3 is used to short circuit the emitter resistance Re, but in fixed bias configuration there is no emitter resistance, so we do not require the bypass capacitor C3. So we will short circuit capacitor C1 and C2 in step number 2, and once you rearrange this circuit, you will have AC equivalent circuit of BJT amplifier. We have obtained this circuit after completion of step number 1. We have obtained this circuit after completion of step number 1. Potential at this point is 0 volts. Potential at this point is also equal to 0 volts, and you can see this branch is having potential equal to 0 volts because it is connected to the ground. So we have just made two changes in this circuit. We have connected this terminal to this branch. You can see here the connection between this terminal and this branch, and we have also connected this terminal to this branch. Here you can see the connection. So this is all you need to do to obtain the AC equivalent circuit. Now we will move to the second step, in which we will replace the transistor with the RE model. We are having common emitter configuration, so the RE model we will draw is for common emitter transistor. This is the final circuit after replacing the transistor with its RE equivalent model. The circuit inside the box is RE equivalent model of the transistor, and we have obtained this circuit after completion of step number 1 and step number 2. Now we will move to the calculation of input and output impedances. Let's say this terminal is terminal 1 and this terminal is terminal 1 prime. This terminal here is terminal 2 and this terminal here is terminal 2 prime. In order to calculate different circuit parameters, we will neglect the source and we will also neglect the load. Let's say the input current is I subscript I and the input voltage is V subscript I. The input voltage is potential difference between the terminals 1 and 1 prime. The output current is I subscript O, and the output voltage is the voltage between terminals 2 and 2 prime. Current through resistance beta plus 1 Re is the base current, and current in this branch is the collector current. Now we will calculate the input impedance. The input impedance is the impedance seen from terminals 1 and 1 prime. The input impedance is represented by Z subscript I, and it is equal to input voltage Vi by the input current II. This is input impedance, and we can easily calculate the input impedance by looking to the input side. Input impedance is equal to resistance RB connected in parallel with the resistance beta plus 1 Re. So Zi is equal to resistance Rb connected in parallel with beta plus 1 resistance Re, or we can say that Zi is equal to Rb beta plus 1 Re divided by Rb plus beta plus 1 Re. This is the final expression of the input impedance. We can also calculate the input impedance by calculating the base current Ib. Zi is equal to Vi divided by II. Vi is the drop across resistance Rb, or drop across resistance beta plus 1 Re. We will consider beta plus 1 Re, and the drop is equal to beta plus 1 Re multiplied with the current flowing through the resistance, which is equal to the base current divided by the input current II. Now we will use the current divider rule to find out base current Ib. By using the current divider rule, the base current Ib is equal to input current II multiplied with resistance Rb, and we already had input current II in the denominator. Inside the bracket, resistance Rb plus beta plus 1 resistance Re. This expression is the expression of base current Ib, and you can see in numerator and in denominator we have the input current, so it will be cancelled out, and Zi is equal to beta plus 1 Re multiplied with resistance Rb. In denominator we have resistance Rb plus beta plus 1 Re, which is similar to this result. So input impedance is equal to resistance Rb connected in parallel with beta plus 1 Re. So this is all for input impedance. Now we will move to the output impedance. The output impedance is the impedance seen from terminals 2 and 2 prime, and the output impedance is represented by Z subscript O. Z subscript O is equal to the output voltage by the output current, and to calculate Z subscript O we need to short circuit the source and we need to open circuit the load. This means voltage source Vs is equal to 0 volts and the load resistance RL is equal to infinite ohms. When Vs is equal to 0, the input voltage Vi is also equal to 0. This implies the input voltage Vi is equal to 0 volts. When input voltage is equal to 0 volts, this means base current Ib is equal to 0 amps. The base current is equal to 0 amps, and when base current is equal to 0 amps, from here you can see the collector current is also equal to 0 amps. This implies the collector current IC is also equal to 0 amps, and when collector current is equal to 0 amps, this terminal will be open circuited, and we already have RL open circuited. So we have the output circuit in which current dependent source is open circuited and the load resistance RL is also open circuited. Two resistances RO and RC are connected in parallel. So we have resistance RO, which is the output resistance of RE model, connected in parallel with the resistance RC, and we can easily calculate the output impedance ZO. ZO is equal to RO connected in parallel with resistance RC, or we can say ZO is equal to RO multiplied with RC divided by RO plus RC. So this is the final expression of the output impedance. Now we will perform few simplifications. We will first simplify the expression of input impedance. Beta is a large quantity, so beta plus 1 is nearly equal to beta, and the resistance beta plus 1 Re is nearly equal to beta times Re. And if resistance Rb is greater than or equal to 10 times beta plus 1 Re, we can neglect beta plus 1 Re from the denominator, and the input impedance is equal to Rb multiplied with beta plus 1 Re divided by resistance Rb. Rb will cancel out, and Zi is now equal to beta plus 1 Re, and this is when the resistance Rb is greater than or equal to 10 times beta plus 1 Re. Now we will simplify the expression of output impedance. Ro is the output resistance of the Re model, and we already know Ro is a large resistance. In case of common ammeter configuration, it is in orders of mega ohms, and in case of common base configuration, it is infinity. So Ro is larger than Rc, and to be more precise, if Ro is greater than or equal to 10 times resistance Rc, we can neglect Rc. So the output impedance is equal to Ro multiplied with Rc divided by Ro, because we have neglected Rc from the denominator. Ro will cancel out, and Zo is equal to Rc, and this is true when Ro is greater than or equal to 10 times Rc. So this is all for this lecture. In the next lecture, we will find out expressions for current gain and voltage gain, and if you have any doubt in this lecture, you may ask in the comment section.